and INSA de Rennes in France. I will present today my work called batch-based end-to-end image-learned codecs using overlapping. This work was supervised by Thomas Guionnet, Sebastien Pelurson, Olivier Deforges, Wassim, Hamidouche, and Meriem, Outtas. So I will start this presentation by introduction to end-to-end learned image codecs. Then I will explain my method called batch-based end-to-end image learned codec using overlapping. I will show then afterwards the results of this method, and I will conclude this presentation with the conclusion and future works. So end-to-end image learned codecs are image codecs that are fully based on deep learning. So they are based on architecture used called the auto-encoder. This auto-encoder has an encoder that takes an image X and transform it to a representation Y. We call this representation a latent representation. It is more compact and it is reduced in the time in terms of dimension. Then we will quantify this representation to y hat. Then we need to generate a bit stream in order to transmit this presentation. For that, we need to apply an arithmetic encoding, and also to do so, we need to know the probability distribution of this latent representation. So that is why we need a probability model. This probability model will estimate this probability distribution of the latent representation. Then we will generate our bit stream, we will transmit it, and at this decoder side, we apply arithmetic decoding, and we have a decoder to reconstruct the input image. So the main or the more famous architecture that it uses on most of the state of the art is shown in this figure. So the probability model that I mentioned before is replaced by an auto-encoder. It is this part, the right part of the figure. This auto-encoder is called the hyper auto-encoder. So after we have our latent representation quantified, we use it as an input to the hyper-encoder that will generate a representation Z that we will quantify and transmit. And at the decoder side, we have a hyper-decoder that will take the reconstruction of Z and estimate the parameter and sigma of a Gaussian distribution, a Gaussian probability distribution that we consider is the distribution of our latent representation. So once we have those parameters, we can generate our bit stream and do our decoding, as I mentioned before. So I need to precise that this architecture is introduced by Ballet. The reference is here, and this kind of architecture is used as a baseline of most of works of end-to-end image learned codecs. So even though this kind of architectures allow us to code multi-resolution image, practically when we code an image that is big in resolution, we are faced to hardware limitation. Mainly, our memory is saturated. For example, if we use a GPU that is RTX 2080 Ti with 11 gigabytes, and we want to code with our end-to-end image learned codec HD image, we cannot do that because we will have an out of memory error, which means that our memory is saturated and decoding cannot be done. So a simple solution to resolve this problem is to divide our image into patches. So when we divide our image into patches, we will use our end-to-end image codec to code those patches, and after that, after we have all the reconstructed patches, we will gather them in order to have the whole decoded image. However, if we do that, we have another problem, which is border artifacts. So the goal of our work is to address the memory saturation problem, which is the hardware limitation, by benefiting from the advantages of patch-based solution, and also by eliminating the border artifacts. So to do so, we will use the patch-based solution, which means we will divide our input into patches, and we will use the overlapping method in order to eliminate the border artifacts. This method also is parallel friendly, which means we can code a number of patches parallelly, and it allows the flexible memory conception. So here on the left we have the steps of our method. So first we have our input. We will divide it into overlapping patches. So to do so, every consecutive patches, two consecutive patches are overlapping on a number of pixels, here noted n, horizontally and vertically, as it is illustrated in the figure on the right. Then when we have all our overlapping patches, we will need a model that is the end-to-end learn codec to code those patches. For that, we used an implementation of Cheng 2020. The reference is here too. It is a model that has the best performance in the state of the art. It managed to be competitive with the VVC, traditional codec for image in image mode, in intra mode. And we did the implementation of this model. We trained it on a data set named Click 2020. We used a training resolution of 256 by 256, and we try to minimize the this loss function, which is the distortion rate, the loss function. D refers to the distortion between the input image, the original image, and the reconstructed one. It is measured either by MSE or SSIM. R is the rate used to transmit the stream, and it is estimated by the Shannon entropy, and lambda is called the Lagrange multiplier. It is a weight between the two. So when we use this model to code our patches, we use also the ability of the GPU to code parallelly multiple patches. And so we do that. We use the parallelization according to the available memory we have on the machine. Here we have the details of the architecture model. So as I mentioned before, there are two auto-encoders, the main one at the left, and the hyper auto-encoder that serves as a probability model on the right. So the hyper auto-encoder are mainly just convolutional layers, and for the main auto-encoder there are residual blacks and attention models. Here we have the details of these modules, and it's mainly also use convolutional layers. So after we have our whole all our patches reconstructed, we need to gather them in order to have the whole decoded image. without the border artifact. So what we do is at the overlapping area, we use a function, a linear function, to eliminate the border artifact. So if we consider that BM, the blue patch, and BM plus 1, the red patch, are two consecutive reconstructed patches that are overlapping on n pixels, the pixel value of the overlapping area PI is the average of the reconstructed patch, the reconstructed pixels of the red patch and the same reconstructed pixel on the blue patch. So this way, it's this way that we eliminate the border artifacts. So after we have all the decoded image gathered, we can after that compute our metrics and evaluate it forward. So to evaluate our approach, we trained 8 models, which means 8 image codecs, 4 for each quality metrics, which means because we use quality metrics MAC and MCSIM, and we used 4 lambda values, which means that which each value corresponds to a different rate. And then we evaluated our approach on the sequences of GVET common test condition, which are videos, and we extract 1 frame from each video. So we compared our method, which is here the third point, which is the patch coding with overlapping, with the number of overlapping pixels going from 2 to 32. We compared this method with the patch coding without overlapping and with the full resolution coding, which means that we coded the whole image. So here we present our results in terms of rate distortion for both MCSIM models and MAC models. So here we have the blue curve, which corresponds to patch-based coding without overlapping, and the black curves correspond to full image coding. And we can see that there is a quite big gap in terms of quality, and this is due to the border artifacts. So we can see that the border artifacts deteriorate the quality of the image. And with our method, we can see that we go back to the same level of the full image coding. So the goal of our method is not to outperform the full image coding, but to be at the same quality while addressing the hardware problem and the memory saturation limitation. In the visual results for MCSIM model here, we can see that there are border artifacts in the patch coding without overlapping, and when we increase the number of the overlapping pixels with our method, the border artifacts are eliminated. So here with n equal to 2, they are still there. With n equal to 4, it's barely there, and with n equal to 8, we cannot see any artifacts. For MEC models, which are the curves at the bottom, we can see that we can observe the same behavior, except that for MAC models, the border artifacts are less visible. If we can see here, the border artifacts are less visible, but with our model, with our approach, they are eliminated completely. So after that, we computed the PD rate gains of our method compared to the full resolution coding, And also we computed the BD rate of the patch coding without overlapping. We did that for MSCIM models, which is the table on the left, and for MSC models, which is the table on the right. So for the table on the left, we can see that we have BD losses, BD rate losses, which is quite big. For patch coding without overlapping, this is due to border artifacts. And when we use our method with 2 overlapping pixels, the loss is still there, but it's reduced. And when we increase the number of overlapping pixels, the loss is not there, and we also have a slight gain. And for n equal to 16, we have a peak of our performance, and when we go to n equals to 32, we can see that the start to decrease, which is normal, because when we increase the number of overlapping pixels, we increase the number of pixels that we code, and at some point the rate will increase, and it will deteriorate our performance. For MSC models, we can see the same behavior mainly. So for patch coding without overlapping, we can see that we have BD rate losses, but it's less important than the MSCIM model. And with only 2 overlapping pixels with our method, we can eliminate the border artifacts. We also measured the complexity of our method and comparing it to full resolution coding. So here, what we did is that we evaluated our method using 2 powerful GPUs. The first one is with 11 gigabytes and the second one is with 24 gigabytes. And when we try to code an HD image on both those GPUs, we have an out of memory errors, which means that we cannot do the coding on those GPUs, and with our method we can do that using even parallelization to optimize the coding time. So for high resolution image such as HD, our method is necessary. For example, for the second resolution, we can see that it is possible to do the full image coding on the second GPU with 24 gigabytes. And in this case, we can see that our the coding time of our method is slightly higher than the coding time of the full resolution coding, which is normal, because in our method we code overlapping pixels, which are additional pixels, and that means we take more time to code them. But we can observe the same behavior for the third resolution. So to conclude this part, we can say that for high resolution image, our method is necessary, and for low resolution method, our method increase the coding time slightly. So to conclude our work, this presentation, our work managed to address the hardware problem of the end-to-end learned image codecs while removing block artifacts. It managed to perform slight gains comparing to full resolution coding. It also increased the coding time slightly if it's for low resolution images. However, for high resolution images such as HD, our method is necessary to do to solve the memory saturation problem. In our future work, we would like to solve or to eliminate the increase of complexity that we cause. So the idea is not to use the overlapping method, but to train our model not only to compress the image, but also to smooth the borders. And for that, we want to change the loss function of our model and add a smoothing term in it that will allow to eliminate the border artifacts automatically. That will be all. Here we have the references that I used, and thank you for your attention. And if you have any questions, do not hesitate.